Hey guys, so this is your wrap-up video for week 3. Thank you for being so patient with this. Just a couple quick things to address for this week's. Okay, so just so you know, when I'm looking at the Top Hat discussion boards, I sort the comments by most liked. So make sure you're liking other people's comments, and that way those questions will come to the top, and I'll make sure to address those things in the wrap-up videos. And also I appreciate the feedback when you guys say, you know, this one was pretty straightforward or this was a little confusing. That's good feedback and I appreciate it. I know a lot of you have been emailing me about you got, a question wrong here, a question wrong there. And so from now on, I'm only going to use multiple choice, the matching, or the click on target. You had something like that in your chemical equations page where you had to click on the reactants or click on the products. And I'll use those types of questions for in-lecture and quiz questions and also test questions so that there's not any, way that you guys can get dinged for a simple mistake like spelling or a space or no space or a capital versus a lowercase. A lot of you were asking for more practice for naming ionic compounds. You're also asking for practice for shapes and bond polarity. So let me just show you what I put up. So if you come to, our Chem 105 homepage, and you can either click on modules here at the button at the bottom, or you can go to the side here and click on modules. And in the first module under the resource headline, let me publish that for you guys, is extra practice. And this was there last week, but I changed the place where that link will take you. And so this one has a little bit more exercises. And so if you go to ionic bonding and simple ionic compounds, in there will be questions if you scroll down about naming. And so there's your polyatomic ions. Here's some give the formulas, complete the tables, and then just some more additional exercises if you guys want to get some extra practice. There's also a link in there for extra practice for shapes and bond polarity. So here's some bonding theory practices. There's some answers, but not all. So if you guys are unsure, please, come to office hours or go with a tutor from the LARC Center, or hopefully you guys are starting to form study groups. All right, so there was a question someone asked about, will we only ever know the charge of a transition metal by looking at an equation? I'm pretty sure you meant formula there. And then, or is there a basic rule for their charges? So no, there's no really, when it comes to the transition metals, there is no kind of rule to figure out the charges. A lot of people know zinc is always 2+ and silver is 1+, but I am not asking you guys to memorize that. And that's the thing, is many of the transition metals can take on different ionic charges. And so that's why we got to kind of let our audience know. So we can look at a formula like iron chloride here. And the thing is, we can look at the periodic table and we know that chloride likes to take on a -1 charge when it forms an ion. So if this is taking on -1 and there's 3 of them, that means there's 3 negative charges. And this is a neutral molecule. Notice there's no plus or negative in the upper right-hand corner. So that means our iron must be balancing the 3 negative charges from the chloride. So when we write the name of this, it becomes iron. And then this is the extra step for the transition metals. We got to put in parentheses what the charge is in parentheses. So we put a Roman numeral 3 in parentheses, and then we put the anion, the chloride. So this becomes iron 3 chloride. And then if we were going the other way, like if we had something like lead, again, we don't know what charge the lead is taking on. Maybe it was 1, maybe it was 1+ or 2+, but because we have in the parentheses, the Roman numeral 2, we know the charge of the lead is 2 plus, right? And we know oxygen always likes to take on a 2 minus charge, okay? So if this lead is 2 plus because of what we see in the parentheses and the oxide's 2 minus because what we know from the periodic table, they'll balance each other in a 1-to-1 ratio. So we know the formula must be PbO for lead oxide. If lead was only 1 plus, right, if there's only a 1 in the parentheses, then we would need 2 leads to balance the oxygen, okay? And so you'll know the charge of transition metal either by looking at the formula, like on the left here, or because it's in parentheses given by the Roman numeral. That tells you the charge of the transition metal. All right, and then a lot of you guys have questions about polar or covalent, and there was so I'm gonna walk you through a molecule. So the first thing, and again, I think you're just that's kind of a weird way to put it, but you were confused about polar covalent versus non-polar covalent, and then, you know, ionic. Of course, if anything is ionic, you'll know that because it's a metal and a non-metal, okay? So now if you're dealing with all non-metals, then we know it's a covalent compound, okay? So if the first step in trying to determine if a molecule is polar is you need to determine if the bonds are polar. And the way we do that is we look at that electronegativity chart, and there's one in your top hat, and I'll give you one on your first test for this class, okay? If all the bonds end up being nonpolar, then you can pretty much stop, because if you have all nonpolar bonds, then your molecule must also be nonpolar, and we call that nonpolar covalent, okay? But if there are some polar bonds, then you need to go through this process, okay? And again, that electronegativity chart, this is a different example, but we're gonna look at H2S, because that was one of the in-lecture questions a lot of you had a question about. So if we look at that, we have hydrogen up here and sulfur on the right here, and 2.2 versus 2.58, the difference between them is 0.38. So that is low enough to tell us that the bonds are non-polar. And so this is a non-polar molecule, but we're gonna just go through this process just so I can clarify some things about that question. Okay, so so you guys had a question about, I asked you a question on your in-lecture about what's the arrangement of the electron pairs, and then the next one was what's the molecular shape. So what's the shape of the electron pairs, and then what's the shape of the molecule, okay? So to answer this question, first we got to determine the number of valence electrons. Of course, we've used the periodic table for that. So we would see hydrogen, right, again, is in this first column, so we know it has 1 valence electron for each one. Sulfur is in this one. Here they're using 16, so we're just going to look at the ones place. And so we know that sulfur has 6 valence electrons. So each hydrogen having 1 valence electron, and there's 2 of them, that gives us 2 valence electrons, 6 valence electrons for each sulfur. So that gives us 6 valence electrons. We add them up, we get 8. The next thing we need to do is draw the Lewis structure. And so we'll put sulfur in the center, put hydrogen on each side, draw a bond to each hydrogen. And remember, each one of these bonds counts as 2 electrons, okay? So we've used 4 electrons here. So out of our 8 total, we only have 4 left. And we're going to put those as lone pairs around the sulfur, okay? Next, we need to determine the number of electron regions. And when we're doing this step, only for this step, a lone pair of electrons counts as an electron region. A single bond counts as an electron region. A double bond counts as an electron region, 1 electron region. As does a triple bond, it counts as an electron region, okay? So they're all kind of the same when we're trying to determine the number of electron regions. So looking at our sulfur here, we have 2 bonds and 2 lone pair of electrons, okay? And so there's 4 electron regions around that sulfur atom. And so from there, we can determine the geometry of the electron regions and also the geometry of the molecule. So if we think about it, I kind of have this little table here. The headings of my columns say the number of electron regions in a bond. So for sulfur, we said there was 4. So we're at one of these guys, okay? Now the number of non-bonding electron regions, meaning electrons that are not involved in a bond, okay? Like these lone pairs above and below the sulfur in my example. So there's 2 regions that are not involved in a bond. So we're here and here. So the geometry of the electron region is going to be tetrahedral because they're going to try, because there's 4 electron regions, they're going to try to space themselves out as far as possible around the atom. But then what's left over when we look at the molecule itself is we get a bent geometry for the molecule, okay? So we get a bent geometry for the molecule. Okay. The only thing is, like we said, it's not, these are not polar bonds, so it doesn't really have a big significance. If we were looking at something like water though, okay, water, if we look at the difference between oxygen here and hydrogen here, well, it's a much bigger difference, right? 1.24. So that's in our region of a polar covalent bond. So that just means that there's a polarity. The oxygen molecule pulls electrons toward it more and pulls them away from the hydrogen. So there's this unequal sharing of electrons. We indicate that with these dipoles shown here. They always point to the more electronegative atom, and then there's like this plus sign on the partial positive charge, okay? And so determining that this molecule has polar bonds, the reason we need to determine the geometry is because we need to figure out if those bonds cancel each other. In the case of water, they do not cancel each other. These 2 dipoles on the left, if we use vector addition, add up to the dipole we see on the right. Okay, and so therefore our molecule is polar. Okay, and again, the example that's always used is carbon dioxide for when it's kind of the opposite, right? In carbon dioxide, we know the bonds are polar this way, right? Our oxygens have a partial negative charge. Our carbon has a partial positive. And so in this way, they're pointing in opposite and equal directions. So they cancel. So this one, the carbon dioxide has polar bonds. However, after going through all those steps, you know, figuring out the valence electrons, drawing the Lewis structure, and then figuring out the geometry of the electron regions, we decide that this is actually a non-polar molecule. Okay. All right, you guys. So thank you for being so patient with me. I have one more page of content I plan on putting out by tomorrow. That would be Wednesday, September 9th. And then I don't plan to put out any more content, and you guys will have your tests next week. So I plan to have all the content out by tomorrow, and I apologize again for delay on that. But you will have, I'll make the due dates, I'll extend them out a little bit more. And so make sure that you're checking that, and I will email you guys. But that way you'll have all your content to go over before your test, which is gonna be next Thursday and Friday. Meaning you can choose when you want to start it, but once you start it, you need to finish it. Also, an announcement, hopefully you watch to the end of the video, for anyone who has not completed an assignment on Top Hat, I went through and I reassigned, again, I'm learning Top Hat, but there's an option there where I can reassign a page, like with all the questions or the homeworks or the quizzes, to any student who didn't answer. Okay, because I know some of you have been emailing me about Wi-Fi issues or just internet access. So I reassigned them to students who did not answer, and you have until September 14th. Okay, so get in there and turn in any work that you haven't already turned in. Okay, There's a couple that were giving me issues. For some reason, it said the whole class didn't turn something in, which I know is not true. So I have an appointment to work with Top Hat on Thursday, and I hope to get that situated. Okay. All right, you guys. I hope you enjoy your night. Take care of yourselves. Check in with each other. Check in with me. Take care.